China's most insane megaprojects under construction aren't just big. We're talking bridges taller than skyscrapers, opera houses that shouldn't be structurally possible, underground power stations carved through mountains, and a canal system that's literally moving rivers across an entire continent. These aren't concepts on drawing boards, they're under construction right now, and the engineering behind them is absolutely insane. Let's start with something that proves cultural buildings can be just as technically demanding as any bridge or dam. Xi'an Cultural Center. You're looking at multiple concert halls, opera houses, and libraries all flowing together as one structure. And here's the problem. Each venue needs completely different acoustics while sharing the same foundation. The opera house can't let sound bleed into the concert hall. The libraries need absolute silence. But they're all structurally connected. Engineers solved it with floating floor systems and triple-layer acoustic barriers that let each building move independently while staying visually unified. The payoff? Perfect sound isolation in flowing architectural forms that look like a single organism. But if that's elegant, the next building is pure structural madness. Shenzhen Science and Technology Museum. Zaha Hadid designed a building with 0 straight lines. 900,000 square feet of continuous curves where every single facade panel is unique. Here's the tension. Traditional structural engineering doesn't work with free-form geometry. Load paths don't follow predictable patterns. Every steel connection node has to be custom fabricated. Computer models are calculating stresses on surfaces that twist in 3 dimensions simultaneously. They're using parametric design software pushed to its absolute limits, manufacturing thousands of different structural components, then assembling them like a massive 3-dimensional puzzle. The result? A building that looks like it landed from another planet. But that's just aesthetic ambition. This next one combines beauty with brutal acoustic science. Shanghai Grand Opera House. 6,000 people need to hear perfect sound inside a building made of flowing curves. That's the challenge Snehetta gave engineers create flawless acoustics inside sculptural chaos. Here's the problem. Curved surfaces reflect sound unpredictably. One wrong angle and you get dead zones or echoing. But the architectural vision demands these cascading wave-like forms. So engineers are embedding acoustic panels directly into the structural concrete, treating the building's ribs and curves as both load-bearing elements and sound-shaping surfaces. Every panel placement requires millimeter precision across massive spans. They're essentially tuning a building like a musical instrument while constructing it. The payoff? An opera house where the structure itself becomes the acoustic system. But acoustic perfection is one thing, building over 1,300 feet tall in a typhoon zone is another level entirely. Shenzhen Hong Kong International Center. Twin towers over 1,300 feet tall in one of Asia's most intense typhoon zones. Wind becomes the primary enemy at this height. Here's the tension. At these elevations, wind doesn't just push, it creates vortices that can make buildings oscillate violently. Engineers are installing tuned mass dampers, designing aerodynamic profiles into the facade, and calculating wind loads that change every 50 feet of height. The structural core has to resist lateral forces strong enough to tear apart poorly designed buildings. Curtain wall systems need to flex without shattering. And they're doing all this while integrating LED facades that turn the entire skin into a light show. The result? Supertalls that can dance with typhoon force winds without breaking. But height isn't everything. Sometimes the real challenge is sheer structural span. Guangzhou Evergrande Football Stadium. 100,000 seats wrapped in a roof shaped like a blooming lotus. The problem? Those petal-shaped roof sections need to cantilever over massive distances without a single column blocking sightlines. Here's where it gets insane. Each petal is a separate structural element spanning hundreds of feet, all connecting to a central tension ring that's holding the entire roof together. The outward thrust is enormous. Engineers are using cable systems and compression rings to distribute loads, essentially hanging the roof from itself. And that golden facade? It's not just decorative, it's part of the structural skin, helping stabilize the geometry while creating the iconic lotus appearance. The payoff? A stadium where architecture and engineering merge into something that shouldn't be structurally possible. But that's one approach to stadium design. The next one takes the complete opposite strategy: Kuzhou Sports Park and Stadium. Mad architects decided to bury a 30,000-seat stadium into the landscape. Half the structure sits below grade, carved into the earth like an ancient crater. Here's the problem. Underground construction means you're fighting water infiltration, dealing with massive retaining walls, and waterproofing systems that can't fail. The roof cantilevers out from earth-sheltered walls, creating this dramatic opening while the load-bearing structure doubles as retention for millions of tons of soil. Engineers are coordinating drainage systems, managing groundwater pressure, and ensuring the partially buried concrete doesn't crack under asymmetric loading from the hillside above. The result? A stadium that looks excavated from nature rather than imposed on it. But building one stadium into landscape is impressive. Building an entire city from scratch is a whole different scale of ambition. Xi'an New Area. They're building a city for millions of people on 300 square miles of empty land, not expanding an existing city, creating one from absolute zero. Here's the problem. You can't just start throwing up buildings. Underground utility corridors have to go in first. Transit infrastructure needs to connect districts that don't exist yet. Foundation work is happening across varying soil conditions simultaneously, and every single building needs to follow unified design standards, while construction crews work on thousands of structures at once. Engineers are using prefabrication at city scale, manufacturing entire building modules off-site, then assembling them in coordinated phases to maintain access roads and staging areas. The result? They're proving you can build urban fabric as fast as individual buildings if you plan the construction like a military operation. But one new city is a coordination challenge. Transforming an entire island requires engineering at a completely different magnitude. Hainan Island. 13,000 square miles of tropical island, becoming China's answer to Hong Kong and Singapore, a massive free trade zone that needs ports, airports, and infrastructure to handle international shipping and millions of tourists. The problem? Every structure has to survive direct typhoon hits. Coastal foundations need to withstand storm surge. Port facilities require underwater concrete pours in brutal conditions. And everything arrives by sea or air, making construction logistics a nightmare. They're building expanded airports, new ports, and bridge connections, all engineered for typhoon-force winds and seismic activity simultaneously. The result? An island-wide infrastructure overhaul that can survive nature's worst while handling global trade. But building on an island is one thing. Spanning a chasm 1,800 feet deep is pure construction madness. Huajiang Grand Canyon Bridge. You're looking at a bridge spanning a canyon 1,800 feet deep. That's taller than the Persian Empire State Building, except you're building across empty air. Here's the nightmare. Tower foundations have to anchor into canyon walls on near vertical set slopes. The main span needs cables supporting a deck across a void where one miscalculation means catastrophic failure. And construction access? Workers are suspended above an abyss, where wind gusts can halt work for days. They're lifting deck sections into position at extreme height, maintaining millimeter precision, over distances where thermal expansion alone can throw off measurements. Cable tensioning has to be perfect, too loose, and the deck sags, too tight, and you overstress the towers. The result? A cable-stayed bridge that cuts travel time from hours to minutes, proving no gap is end. Too wide to span. But if that's conquering vertical space, the next project goes underground at a scale that seems impossible. Yarlung Tsangpo, Medog, HRA Power Megaproject. They're carving a power station inside the Himalayas capable of generating 60 million kilowatts. That's 3 times the output of the Three Gorges Dam, except this one's completely underground. Here's the insanity. They're excavating caverns large enough for turbine hulls inside mountains. In an active seismic zone, tunnel boring machines are drilling through rock at extreme altitude, where oxygen levels slow everything down. Diversion tunnels have to route an entire river through solid mountain while construction happens. The river drops 16,000 feet through this canyon. Managing that kind of pressure requires penstock engineering at scales never attempted before, and every ton of concrete, every piece of equipment, has to be transported into one of the most remote locations on Earth. The result? If completed, the world's largest hydropower station proving you can harness entire river systems by drilling through mountains. But moving water through turbines is one challenge. Moving entire rivers across a continent is engineering on a completely different level. China, South, North, water. Transfer. 1,800 miles of canals, moving entire rivers from south to north. They're in Tunham. Solving northern China's water crisis by redirecting southern river systems across the continent. The problem? They're tunneling under the Yellow River, building aqueducts across valleys, and boring through mountains, where flooding can destroy years of work. Pump stations have to lift billions of gallons over elevation changes, and every kilometer crosses different soil conditions, and seismic zones requiring custom engineering solutions. They've already completed sections moving billions of gallons daily. Flow control structures operate at scales that dwarf dams, managing pressure and flow across climate zones. The result? 400 million people getting water from rivers hundreds of miles. A way proving you can literally move nature's plumbing. But moving water is one thing. The next facility is built to teach the science behind all this. Engineering. Xi'an Science and Technology. Museum. Exhibition spaces requiring column-free spans so visitors can see displays without structural interruptions. Plus, a planetarium dome that needs perfect geometry and zero vibration. The challenge? Integrating climate control systems that keep artifacts safe while maintaining visitor comfort in tropical heat, acoustic isolation between interactive exhibits, and quiet learning. Spaces. And lighting systems that don't interfere with planetarium projections or damage. Sensitive displays. Engineers are embedding all mechanical systems, HVAC, electrical, fire suppression, into the problem. Architecture. Without compromising the exhibition design, the planetarium dome requires precision concrete work where millimeter-level errors ruin projection quality. The result? A building where every structural decision serves education, proving museums need engineering just as sophisticated as the science they display. But all these buildings needs one critical thing: massive energy storage. Luxy pumped storage power station. 2 reservoirs at different elevations, turning mountains into a giant battery. 3,600 megawatts of storage, using nothing but gravity and water. Here's how it works. Pump water uphill when there's excess solar and wind power, release it downhill through turbines when the grid needs electricity. But the engineering challenge is brutal. You're excavating an underground powerhouse large enough for reversible turbine generators, drilling tunnels connecting upper and lower reservoirs, and building dams that can handle the pressure of water being pumped both directions. The penstock pipes managing water flow have to withstand extreme pressure cycling. The underground caverns need ventilation systems for workers and equipment. And everything's carved through rock that has to remain stable in a seismic zone. The result? A mountain transformed into energy storage that makes renewable power viable, proving the future of electricity isn't just generating it, but storing it at scales that seemed impossible. These 14 projects aren't just construction sites. They're proof that engineering limits exist only until someone figures out how to break them.